So, guys, in this video, we're going to continue solving these trig equations. Uh, find all values of theta in the interval 0 less than or equal to theta less than 2 pi that satisfy the following equations. Give exact values. And each one of these problems does not require a calculator. Okay, so let's take a look at example 4 here. Tan theta plus 2 tan theta times sine theta is equal to 0. So for this problem here, all right, you probably notice that, well, there's a tan theta in both of these here, and that's exactly what we're going to do. We're going to factor it out like a GCF. It's not a quadratic equation, but it's another type of a solving by factoring problem. All right, so we can factor out a tan theta from each of these terms here, and we're left with, after we factor out a tan theta, 1 plus 2 sine theta, and they're both equal to 0. So what we can do from here, we actually have our terms that we can essentially set equal to 0. So we have tan theta is equal to 0, and then we have 1 plus 2 sine theta is equal to 0 as well. So now both of these are unit circle values, and we're just basically figuring out where they occur. So where is tangent equal to 0? Well, it's equal to 0 at 0 and at pi units. Okay. It also is equal to 0 at 2 pi, but remember, it's non-inclusive of 2 pi. So we're just left with 0 and pi here. And then if we were to solve for sine, here sine theta is equal to -1/2. So this is again in quadrants 3 and 4. This occurs at 7 pi over 6 and 11 pi over 6. So we have 4 unique solutions here for example 4. All right. Taking a look at example 5, we have 2 cosine squared theta plus 3 sine theta minus 3 is equal to 0. And we have to examine the fact that there are 2 trig functions, cosine and sine. But cosine squared, we can use one of the Pythagorean identities to rewrite it so that way everything is in terms of sine. All right, so I'm going to take a second and rewrite that term. All right, so I just boxed in the cosine squared, and using the Pythagorean identity, sorry, I just had to fix it. It should be 2 times 1 minus sine squared. So that's replacing cosine squared. So 2 times 1 minus sine squared theta plus 3 sine theta minus 3 is equal to 0. So we'll distribute the 2. We'll have 2. So it'll become 2 minus 2 sine squared. 2 sine squared theta plus 3 sine theta minus 3 equals 0. We can combine 2 minus 3. We'll have -1. So we'll have -2 sine squared theta plus 3 sine theta minus 1 equals 0. Again, I don't like the leading coefficient to be negative. You don't have to do this if you don't want to. I'm just kind of neurotic with that. Minus 3 sine theta plus 1 equals 0. So now this just becomes like a quadratic trig equation that we solved before. A times C. So we're multiplying the leading coefficient times a constant. So 2 times 1 is 2. Factors that multiply to 2 add to -3, -2, and -1. So we'll have 2 sine squared, and now we can factor by grouping. 2 sine squared theta minus 2 sine theta minus 1 sine theta plus 1 equals 0. Factor by grouping here. We can factor out a 2 sine theta times sine theta minus 1, and then minus 1 times sine theta minus 1 equals 0. Our two binomial terms. So I'm just going to insert a new slide here and continue this work on the next slide. So I'm going to add a new slide in here. So the 2 sine theta this times sine theta minus 1 times sine theta minus 1 equals 0. I'm going to factor out the sine theta. So this is example 5 continued. Is going to be sine theta minus 1 times 2 sine theta minus 1 equals 0. So you're just left with sine theta equals 1. And then when you solve for sine theta here, sine theta is equal to a half. So sine theta is equal to 1. That occurs at pi over 2, the top of the unit circle. And then sine theta is equal to a half at pi over 6, quadrant 1. And then in quadrant 2, it's at 5 pi over 6. So we have 3 unique solutions here. Much better. Okay. All right, so let's go to example 6 here. We have 2 cosine theta plus sine of 2 theta is equal to 0. So again, this is not in terms of one trig function, but sine of 2 theta is a double angle formula that we can rewrite it. So let me take a little bit of time and substitute the double angle formula into the equation. So I just replaced sine of 2 theta with its respective double angle formula. And this actually turns out just very similar to what we had in example 4, where we're just going to have to essentially factor out a GCF. So let me duplicate this here. This is just essentially another GCF problem. And in this case, the GCF is 2 cosine theta. So we'll have 2 cos theta times, and then we'll have 1 plus sine theta is equal to 0. Two cos theta equals 0. 1 plus sine theta is equal to 0. So we'll have cos theta is equal to 0. That occurs at pi over 2. Let me write theta. At pi over 2 and at 3 pi over 2. So those are our two solutions there. And then sine theta equals -1. So, well, that's at 3 pi over 2. That's already included in this first set of solutions here, so you don't need to repeat it, okay? So I just included that note there. Already include with cos theta is equal to 0, so you don't need to kind of rebox it in. And then this last example here that, again, no calculator is required. We have 2 times sine of 2 theta is equal to negative radical 2. They're actually... All right, so this one we're going to solve a little bit differently here because of the fact that we have a coefficient 2 here. So what we can do to solve, to start, we can divide both sides through by 2. So we'll have sine of 2 theta. Sine of 2 theta is equal to negative radical 2 over 2. Okay. And what we can do from here is take the sine inverse of both sides. Okay. So when we take the sine inverse of both sides, sine inverse and sine cancel out, and you're just left with 2 theta is equal to sine inverse of negative radical 2 over 2. Sine inverse of negative radical 2 over 2. Now, this looks like a unit circle value. Okay, so that's why, again, there's no calculator required from here. And this occurs if it's negative in quadrants 3 and 4. So what we can do to solve for theta, again, we're trying to find the values of theta. To solve for theta from here, we're going to set each one of these values. We're essentially going to have 2 separate kind of linear trig equations. We'll have 2 theta in quadrant 3. It's going to be equal to 5 pi over 4. And then in quadrant 4, it's going to be equal to 7 pi over 4. Okay, so we just have essentially 2 separate trig equations here. And then now we'll have theta. We would divide by 2 here. So dividing by 2 is the same as multiplying by a half. So our first solution is going to be theta is equal to 5 pi over 8. And our second solution is going to be theta is equal to 7 pi over 8. Okay, so those are 2 solutions here. Now keep in mind that our solutions, we're finding all values in the interval 0 less than or equal to theta less than 2 pi. And if we look at these first 2 solutions, 5 pi over 8 and 7 pi over 8, especially 7 pi over 8, this one's probably pretty clear. That's still less than pi. So we actually have another set of solutions to get to. Now, what we can do, if you recall from the previous section, to find the general solutions, right? What we can do is add 2 pi to each one of these first set of solutions to find any other additional solution. So that's what we're going to do next. So I made a note here how to find the coterminal angles by just adding 2 pi to the initial set of solutions. So we'll have 13 pi over 4 as our second possible. And then if it's coterminal with quadrant 4, we would add 2 pi to 7 pi over 4, which will give us 15 pi over 4. So what we have from here essentially is we're going to have 2 separate sets of solutions here. So if we continue using this, we're going to say that 2 theta can also equal 13 pi over 4. And 2 theta can also equal 15 pi over 4. So dividing by 2 is the same as multiplying by half. So our third and fourth solutions. So this is going to be 13 pi over 8. And then theta is going to be equal to 15 pi over 8 here for this problem. Okay. And the reason why, again, we did that because our solutions here, we have to find all the values that are contained between 0 to 2 pi. So we kind of connected the general solutions from the previous, the beginning of the, with the linear trig equations to this example as well. I also wanted to note how we can also apply some previous knowledge for example 7. I'm going to do it on the next slide. All right, so on this slide here, we're just kind of showing you another way that we can think about finding all the solutions for this trig equation. So we have the same setup that we did before: divide by 2, take the sine inverse, and then set 2 theta each one to each one of these unit circle values, and we get these first two solutions: 5 pi over 8 and 7 pi over 8. Now, I want you guys to recall the fact from before, sine of 2 theta. If we think about graphing the trig equation, that recall that the period of a trig function is 2 pi divided by b. So the periodicity, I think that's actually a word, period is equal to 2 pi, and in this case it would be divided by 2. So the period of this function is technically equal to pi. So what we could do is take our first set of solutions and then find the next value would be 5 pi over 8 plus pi. So plus pi there would be equal to 13 pi over 8, right? Because this would technically be 8 pi over 8 as like a fraction. So this would give us 13 pi over 8 for this solution. And then we could technically do 7 pi over 8 plus pi as well to give us theta is equal to 15 pi over 8. Okay, so that's another way to find the solution, is to use the period of the sine function to find additional solutions. All right, and then our restriction was just that it had to be between 0 to 2 pi. So if either way, we had to, without a calculator, again, no calculator was required for any of these. We had to connect either using the general solution concept to find the additional answers, or if you recognize the fact that we could have also used the period of the function to find additional solutions. Either way will work, right? And I'll just make an additional note that there's an additional way on the next slide here. All right, so these are 4 non-calculator problems that we can solve with quadratic trig equations and equations with multiple functions.